Welcome to this comprehensive lecture on PyTorch RMSNorm, or Root Mean Square Layer Normalization. In this session, we're going to explore a powerful normalization technique that's becoming increasingly popular in modern neural networks, especially in large language models. Our learning objectives are to understand the mathematical foundation of RMSNorm, learn how to use torch.nn.RMSNorm effectively, compare it with LayerNorm, apply it in practical neural network architectures, and explore its performance benefits and use cases. Let's start with an architecture overview. RMSNorm is essentially a simplification of LayerNorm that maintains similar performance while being computationally more efficient. As you can see in this diagram, RMSNorm simplifies the normalization process by removing the mean centering step that's present in traditional LayerNorm. This architectural diagram shows how the input flows through the RMS calculation, normalization, and optional scaling steps. The key insight here is that by removing the mean subtraction, we reduce computational complexity while maintaining the stabilizing benefits of normalization. Now let's look at a direct comparison between RMSNorm and LayerNorm. This visualization clearly shows the mathematical differences between the two approaches. LayerNorm computes both mean and variance, then normalizes by subtracting the mean and dividing by the standard deviation. In contrast, RMSNorm only computes the root mean square of the values and normalizes by dividing by this RMS value. This simpler approach means fewer operations, less memory usage, and faster computation, especially at scale. The diagram illustrates how RMSNorm achieves similar normalization effects with a more streamlined computation path. Let's begin our hands-on exploration by importing the necessary libraries. We'll need PyTorch for the neural network operations, NumPy for numerical computations, Matplotlib and Seaborn for visualizations, and some typing utilities for better code clarity. I'm also setting up our visualization style and random seeds to ensure reproducibility throughout our experiments. Let's dive into the basic usage with the simplest possible example of RMSNorm. This section will help you understand how to get started quickly. Here we're creating our first RMSNorm layer. I'm initializing it to normalize over the last dimension with size 10. Then we create a simple input tensor with batch size 4 and 10 features. When we apply RMSNorm to this input, it normalizes each sample independently across the feature dimension. Notice how the output maintains the same shape as the input, which is exactly what we expect from a normalization layer. I'm also adding assertions to verify that our shapes match and that we don't have any NaN values in the output. Perfect! We can see that the input and output shapes are identical, both with batch size 4 and 10 features. The normalization has been applied successfully, transforming our input values while maintaining the tensor structure. Notice how the normalized values have a different scale compared to the original input. This is the effect of the RMS normalization. Now let's dive deeper into understanding the mathematical operation behind RMSNorm. The formula shows that we divide the input by its RMS value and then multiply by a learnable scale parameter gamma. The RMS, or root mean square, is calculated as the square root of the mean of squared values plus a small epsilon for numerical stability. To really understand what's happening under the hood, I'm implementing RMSNorm manually. This educational implementation shows exactly how the normalization works. First, we calculate which dimensions to normalize over based on the normalized shape. Then we compute the RMS by taking the mean of squared values, adding epsilon for stability, and taking the square root. We divide the input by this RMS value to normalize it, and finally apply the learnable weight parameter if provided. Let me compare this manual implementation with PyTorches built in RMSNorm to verify they produce identical results. Excellent! Our manual implementation perfectly matches PyTorch's RMSNorm, confirming our understanding of the algorithm. The visualization shows how RMSNorm transforms the distribution of values. Notice how the original values on the left have a wider spread, while the normalized values on the right have a more controlled distribution. The mean shifts closer to 0, and the overall spread is more consistent. This normalization effect helps stabilize training in deep neural networks. Let's explore the complete parameter documentation for RMSNorm. This table provides a comprehensive overview of all parameters you can configure. The normalized shape parameter is required and determines which dimensions are normalized. The EPS parameter provides numerical stability with intelligent defaults based on your data type. The Elementwise Affine parameter controls whether we have learnable scale weights. Device and D-type parameters let you control where and how the computation happens. Understanding how each parameter affects the output is crucial for effective usage. Now let's explore the normalized shape parameter in detail, as it's crucial for controlling the normalization behavior. Here I'm demonstrating 3 different ways to specify the normalized shape parameter. You can use a single integer to normalize just the last dimension, a list to normalize multiple trailing dimensions, or a torch.size object for the same purpose. Notice how PyTorch internally converts all these formats to a consistent tuple representation. As we can see, PyTorch flexibly accepts different input formats but internally stores them as tuples. This consistency makes it easier to work with the normalized shape regardless of how you initially specified it. Let's see how different normalized shape values affect the actual normalization. I'm creating a 3D tensor with batch size, sequence length, and hidden dimension. When we normalize over just the last dimension, each position in the sequence is normalized independently. But when we normalize over the last 2 dimensions, we're normalizing across both the sequence and feature dimensions together. This gives us very different normalization scopes. Perfect. The outputs confirm that different normalized shape values produce different results, as expected. When normalizing just the hidden dimension, we preserve more of the sequence structure. When normalizing over both sequence and hidden dimensions, we get a more global normalization. This flexibility allows you to choose the right normalization scope for your specific use case. Understanding the EPS parameter is crucial for numerical stability, especially when dealing with very small values. I'm demonstrating how different epsilon values affect numerical stability when dealing with extremely small input values, close to the limits of floating point precision. We create inputs with values around 10 to the negative 10, then apply RMSNorm with different epsilon values ranging from very small to relatively large. This experiment shows how epsilon prevents division by values that are too close to 0. The visualization clearly shows how epsilon affects stability. With very small epsilon values on the left, we might get numerical instability when inputs are near 0. As we increase epsilon, the outputs become more stable and predictable. The larger epsilon values provide a safety buffer against numerical issues. The key takeaway is that larger epsilon values provide more numerical stability for near 0 inputs, though you typically don't need to adjust the default unless working with extreme value ranges. Let's explore the Elementwise affine parameters that give RMSNorm additional expressiveness. Here I'm comparing RMSNorm with and without affine parameters. With affine parameters enabled, which is the default, we get learnable weight parameters initialized to 1. These weights allow the model to learn feature-specific scaling. Without affine parameters, we have no learnable parameters at all, just pure normalization. To demonstrate the effect, I'm manually scaling the weights, doubling the first 5 features and halving the last 5. The visualizations clearly show the impact of affine parameters. In the left plot, we see how the scaled affine weights create different standard deviations for different features, while without affine parameters, all features have similar spreads. The right plot shows our manually set weight values, with the first 5 features scaled to 2 and the last 5 scaled to 0.5. This feature-wise scaling capability is crucial for model expressiveness, allowing the network to learn which features should have larger or smaller magnitudes. Let's analyze how gradients flow through RMSNorm, which is crucial for understanding its training dynamics. I'm creating 2 simple models, one with RMSNorm and one without, to compare gradient flow. Each model has 2 linear layers with an optional normalization layer in between. After computing a simple loss and backpropagating, we can examine how the gradients differ between the 2 architectures. The gradient statistics and distributions reveal important insights. With RMSNorm, we see more controlled gradient values with a tighter distribution around 0. Without RMSNorm, the gradients can have more variance and potentially more extreme values. The histograms clearly show that RMSNorm helps stabilize gradient flow with a more concentrated distribution. This stabilization effect is one of the key benefits of normalization layers in deep networks. Our verification confirms that gradient flow is stable through RMSNorm with no nan or infinity values. Now let's see RMSNorm in action within a practical transformer-style architecture. I'm implementing a simplified transformer block using RMSNorm. This block includes multi-head attention and a feed-forward network, with RMSNorm applied after each sublayer. This is similar to how modern transformers like Llama use RMSNorm instead of LayerNorm. The architecture follows the standard pattern of attention, add and norm, then feed forward, add and norm. Notice how we're using RMSNorm for both normalization steps. Excellent, our transformer block is working correctly. The output maintains the same shape as the input, which is essential for stacking multiple transformer blocks. The output statistics show well-behaved values with a mean near 0 and standard deviation close to 1, indicating effective normalization. The min and max values are reasonable, showing that RMSNorm is preventing value explosion or vanishing. This demonstrates how RMSNorm integrates seamlessly into modern transformer architectures. Let's simulate a training scenario to see how RMSNorm performs in practice. I'm creating a synthetic dataset for sequence classification. This helper function generates sequences with different frequency patterns for each class, giving us learnable patterns that our model can distinguish. The data has temporal structure with class-specific characteristics, making it a good test case for our sequence classifier. Now I'm building a sequence classifier that uses an LSTM followed by RMSNorm and a classification head. We'll train two versions, one with RMSNorm and one with LayerNorm, to compare their learning dynamics. The model processes sequences through the LSTM, normalizes the final hidden state, and then classifies it. I'm training both models for 20 epochs on our synthetic data to see how they compare. The training curves reveal interesting insights. Both RMSNorm and LayerNorm successfully learned the patterns, with loss decreasing significantly from the initial values. The curves are quite similar, showing that RMSNorm achieves comparable training dynamics to LayerNorm. In some epochs, RMSNorm even shows slightly better loss values. The key takeaway is that RMSNorm provides effective normalization for training while being computationally simpler. Both models successfully learned to classify our synthetic sequences, validating that RMSNorm is a viable alternative to LayerNorm. Let's compare the performance of RMSNorm versus LayerNorm. Although RMSNorm is known to be faster than LayerNorm for large neural networks on GPU, our experiment will show what happens on CPU, which might surprise you. I'm creating a benchmarking function to measure the execution time of both normalization methods. We'll test different input shapes to see how performance scales with different tensor sizes. Now let's run comprehensive benchmarks across different tensor shapes, from small batches to sequence data similar to what you'd see in transformer models. We'll measure execution time for 100 iterations to get reliable timing results. Interesting results. On CPU, we're actually seeing that RMSNorm is slightly slower than LayerNorm, which might seem counterintuitive. The performance comparison shows negative speedup percentages, meaning LayerNorm is faster in our CPU environment. This is different from what we typically see on GPUs with large models, where RMSNorm shows significant speedups. The execution time differences are relatively small but consistent across different input shapes. This demonstrates an important point. Performance characteristics can vary significantly between CPU and GPU execution. On GPUs, especially with large models, RMSNorm typically shows meaningful speedups due to its simpler computation. Let's explore advanced usage by creating a custom RMSNorm implementation with additional monitoring features. I'm implementing a custom RMSNorm class that includes running statistics for monitoring. This implementation adds momentum-based tracking of the RMS values across batches, which can be useful for debugging and analysis. The core normalization logic remains the same, but we're adding extra bookkeeping to track how the normalization evolves during training. Let me verify that our custom implementation matches PyTorch's standard RMSNorm. Perfect. Our custom RMSNorm implementation matches PyTorch's version, confirming our implementation is correct. The running RMS value of approximately 1 makes sense for normally distributed input data. This custom implementation demonstrates how you could extend RMSNorm with additional features like statistics tracking, custom initialization schemes, or specialized behavior for your specific use case. Let's cover common pitfalls and best practices to help you avoid issues when using RMSNorm. I'm demonstrating several common pitfalls and their solutions. First, using the wrong normalized shape will cause a runtime error, so always ensure your dimensions match. Second, numerical stability is crucial. Setting epsilon to 0 can be dangerous with very small values. For best practices, I'm showing shape verification helpers and gradient clipping techniques that work well with RMSNorm. Great, we've covered the key pitfalls and solutions. The shape mismatch error shows exactly what happens when dimensions don't align. Interestingly, even with extremely small values, modern PyTorch handles numerical stability well, though it's still best practice to use appropriate epsilon values. The shape verification helper provides a safety net to catch dimension mismatches early. Gradient clipping works seamlessly with RMSNorm, helping maintain stable training. These practices will help you use RMSNorm effectively in your projects. Let's wrap up with a comprehensive summary and best practices guide. RMSNorm is a simpler, more efficient alternative to LayerNorm that's becoming increasingly popular in modern architectures. The key advantages are computational efficiency through simpler math, no mean centering which reduces operations, and fewer parameters with only scale and no shift. Use RMSNorm in large-scale transformer models, when training speed is critical, in resource-constrained environments, and models with many normalization layers. For best practices, always use appropriate epsilon values, verify tensor shapes match, keep Elementwise Affine enabled for model expressiveness, combine with residual connections in transformers, and monitor gradient flow for stable training. Remember that RMSNorm is most beneficial for large hidden dimensions over 256. Speedup is more noticeable on GPU than CPU, and you can often replace LayerNorm with RMSNorm in existing models for improved efficiency. That's all for our comprehensive exploration of PyTorch RMSNorm. Thank you for joining me in this deep dive into one of the most important normalization techniques in modern deep learning.